And my talk today will be a music everybody knows, no? Multi-controlled unitaries from many-body angular momentum interactions and some kind of magic, no? Okay? So I will be talking about how to implement this multi-controlled unitaries. So the topics are organized in this fashion. I will give a brief overview of what is known. Then I will talk about the, for D-level systems of roughly about the qubit Clifford and T-gates, okay? Then I will talk about the angular momentum representation that I want to do here, is the work here. And if I have time, I will talk about gate decompositions and the quantum optics analog, okay? And give some future perspectives for this work, okay? Let's go, okay. So this work is based on something I released this week on Archive. Someone is interested, they can see, okay? And the motivation in broadly is these models, quantum information, these models of quantum computation, magic states and gates, the Gottesman-Kneel theorem, relations to foundations of physics, and many more. Some recent works, so more recently we have some advantage from instead of using qubits, using higher level systems like qubits, we call qubits, so D-level systems, and or using any-body interactions, okay? And my motivation is more on the side of physics, okay? So many-body physics, especially multipartite entanglement, quantum optics, and so on, atomic physics, and stuff like that. So an example of my interest on the community as well is this spin chirality, for example, and works by Xiaogang Guan on this topological phase transitions, stuff like that, okay? Using long-range entanglement, so I'm kind of pursuing this, okay? This line of reasoning, okay? So let's start reviewing some stuff. I will talk quickly, I don't have so much time, but the local polygroup is spanned by these Z and X matrices, Pauli matrices, okay? So, I'm talking qubits now, okay? And the local Clifford group, by its turn, is spanned by this H matrix, is the Hadamard matrix, generates superpositions, for example, and this S matrix, okay? And the idea here is that the local Clifford group brings a Pauli matrix into a Pauli matrix, okay? So it's, in group theory, is called the normalizer subgroup within the full SU2 subgroup, okay? Group, okay. So another kind of gate is the so-called magic gates, okay? So the main example, perhaps, is this T gate, okay? Or pi above 8 gate, okay? So it has to do with these magic states, let me point, that are in these special directions, these magic directions, they call, with a magic angle that will appear sometimes here, okay, in the presentation. And this non-Clifford gate, for example, brings the Pauli matrix, a Pauli gate into a Clifford gate. So we say we are going higher in the Clifford hierarchy, in some sense, okay? And the other speakers can correct me if I say something silly here, okay? And entering in the topic of what I want to talk about, we have these 2-qubit gates that are they are similar to a if operation in programming, yeah. So it works like that. If W is a unitary, you can form like the controller W, okay? So controller W is the following. If it's 0, okay, do nothing, okay? And if it's 1, apply W, okay? So for example, the control not is the control X, okay? So 0 does nothing, 1 apply the gate X. The control phase is the control Z, okay? So 0 does nothing, 1 applies Z, okay? And these are the building blocks of quantum information, okay? So it's important to find a way to deal with, handle this, okay? So, and interesting stuff is that if you act locally with the Clifford group, okay, of unitaries, you can map, for example, the control phase into the control knot, okay? There's exploding literature, experimental literature, on how to implement with high fidelities this, okay? This kind of gates. Okay. We have as well for example, I can do the control of a gate, okay? So it's a recursive definition, okay? And so it's a 3-qubit gate, 3-particle gate. And the idea is simple. For example, the Toffoli gate, that's very important in the subject, is the control knot, okay? We have as well the control phase, and you can go for more particles with this scheme, yes? So define recursively in this fashion, okay? And the problem is how, the problem I want to tackle here is how to implement these gates, but in a general way, okay? So I want to use this many-body angular momentum or spin interactions to implement this kind of gates because they are important, and this way I can do for many systems, for example, spin orbit coupling, or using spin orbit coupling, or dipole coupling, or like in Heisenberg model or stuff like that, okay? So this is my idea. No? And let's talk quickly here. The generalization for D-level systems, so-called qubits, we have the local poly group that's spanned by these analogous Z and X gates, where I have the definitions here. If you have questions later on, you can ask. And these two gates are connected via the discrete Fourier transform. So the acronym is not very good. It's DFT, but it's nothing to do with the density functional theory. But so it's, you can picture when the dimension is a power of prime, okay? You can picture this in a discrete phase space, okay? These operations. So, so in this picture, you have these kind of symplectic gates, okay? Which form you can span the local Clifford group, okay? In this dimension. And so the skew Q vector, for example, for Q treat is 0, 1, or 2, and then acts like you see as a position this in a grid, and then the momentum states are the Fourier transform of this, okay? But in a discrete phase space picture. So example for Q-treats, the Z-gate in the computational basis has this form. This omega is this third root of unity, okay? So omega cube is 1. And this, the X-gate is given by this, okay? And we have alternative kind of Clifford gates are more convenient for circuit design, for example. And the Q-treat analogous of the T-gate is this gate here, okay? And then we can form these two Qubit controlled unitaries, for example. Since you have an extra level, level 2 here, it works like this. If it's 0, does nothing. 1, you apply W, and 2, you apply W twice. Okay, so then you can construct three Qubit controlled unitaries and so on. Okay, and you can also consider for design of the quantum circuits some hard controlled quantum gates. So I would take an example. This 1 W, you just apply if it's 1, okay, in the other subsystem, okay? And you can construct these multi-controlled QD unitaries from the Pauli or Clifford groups, okay? And the interesting thing here is that this Clifford plus the set of gates, they are approximately universal, okay? So you can approximate any body gate unitary by combinations of this, okay? By suitable combinations of this, okay? So entering this angular momentum representation that I want to do, I will take a start simple here. For j equals 1, so 3-level system, you can think like a particle of spin 1, yeah? So Jz, the gate, the observable Jz, is this, but in this ordering, in this angular momentum ordering, okay? In the angular momentum basis, okay? So a z rotation in this picture is just exponentiation of this Jz, and is a diagonal operator, so it's very simple. So if you put this special angle here, there's not this I here, it's 2 pi above 3, you get this gate, which is almost the Z gate, yes? So the idea is that we, if we do this encoding according to we reorder the bases a little bit, you will get the Z basis. So the Z gate is, you can see as simply a rotation with this special phase, 2 pi above 3, okay? Z square, 4 pi above 3, okay? And what about x and x square so if you want to construct the full Pauli group, you apply the Fourier transform, okay? So you will fall in this, is a kind of rotation of this observable here, which is the so-called Peg-Barnett Hermitian phase operator, which is related to a big problem in foundations of quantum mechanics, which is to define Hermitian phase operator in quantum mechanics. This is the Dirac phase problem for whoever is interested. So we can see that Jz and theta z are the infinitesimal generators of the Qubit local Pauli group, okay? So very important stuff here in quantum optics and stuff like that. And so another kind of magic stuff appearing here, or the magic angle appearing in other contexts, is that for Qubits you can see this Peg-Barnett phase operator as this combination of this kind of quadrupole stuff and dipole stuff with this special magic angle, yes? And this special magic angle, this paper is very cool, appears in many contexts in nature, like nuclear magnetic resonance. You have this spinning in the magic angle, yeah? So I think some octopus have the fibers of them, in many contexts this kind of magic angle appears, and it will appear again here. Okay, and the Qubit Clifford gates, they are kind of a squeezing like a Gaussian stuff, okay, on these operators, except for this Clifford gate, which is that permutation gate from before. It's a very simple expression, okay, and this T gate, surprisingly, is a simple expression as well, okay. We have here theta z square is a kind of Lipkin-Meshkov-Glick Hamiltonian, okay. I think that is wrong here, okay. So how do we represent the 2-qubit controlled unitaries? This kind of dipole coupling is very common in physics. So, and if you develop here, you will see that with the unitary corresponding to this, or the evolution of this kind of interaction, is a controlled Z rotation. Yeah? So, and so if you apply this this in general for integer J, okay? If you apply, if you put this special phase angle here, 2 chi pi above d, you get exactly the controlled phase gates, okay? All the hypotheses. And if you apply the local DFT, the Fourier transform, you get a kind of coupling between angular momentum and phase angular position, okay? And for j equals 1, you have a simplification, you get a kind of dipole-quadrupole interaction, okay? Which appear in some contexts. And the multi-controlled unitaries for 3 qubits, for example, you get this, this 3-body gate comes from this very interesting 3-body angular momentum coupling, okay, in Z. And so for any qubits, you get this main result, some sense, that all the control Z gates are this evolution of this any qubit angular momentum interaction, okay? So it's a very elegant, okay, expression, I think, here. And we can obtain the other gates applying suitable local operations in these diagonal gates, okay? So let's see how much time I have. I think 10 minutes. So maybe the problem with this kind of interaction is that first, in theory, is not very. We are not very familiar to working with this. Okay, with few exceptions or this from previous slides, but and also experimentally is not the most trivial stuff. Although recently there are some experimental realization of stuff like this, but for qubits, okay? So the idea of we can decompose, for example, a 3-qubit gate in terms of more familiar stuff, okay? So in terms of 2-qubit gates, sequences of 2-qubit gates. So what I'm saying is, broadly speaking, is grossly speaking, is I can, for example, in some sense, I can decompose a 3-body interaction in terms of 2-body sequence of 2-body interactions that we know better. Okay, so Ising or some stuff like that, okay, nearest neighbors, okay? And this for me is very pretty, actually, it's a little bit. Because this, in my personal opinion, this justify in some sense the whole endeavor of quantum information, because you are decomposing something of interactions of three or more bodies into this sequence of 2-body interactions, okay? So if you think computationally, if you think physics computationally, you get new physical results, in my view, okay? So this is for qubits, unknown decomposition, and this for qubits, but there are many more, okay? And the quantum optical analog, I will talk fast. You can make for qubits, you can do a three-rail encoding, very simple here in some sense. And there's this new many modes Jordan-Schwinger map. So you map this angular momentum picture into a quantum optics picture, okay? And so the Q-treat DFT, the Fourier transform, I can decompose in this way, is another technique. But, and so this, as the product of four unitaries, and these three here, they are very simple because they are just phase shifts or balanced beam splitter operations. But this is this third one that is here, okay, has this magic angle again, okay? So it appears again, okay, in a completely different context. And this is the diagram for the Q-treat Fourier transform, okay? And then in general, I won't explain everything here, but to couple the subsystems, we can, using the Jordan-Schwinger map, we can, via this cross-care interaction, implement, for example, this is a diagram of the hard control Ctrl Z. Hard control Ctrl Z. This is the other hard control Ctrl Z. And so if you your single photos enter here and follow here, you will have the Ctrl Ctrl Z. Okay, so this three body unitary. Okay, so it's a proof of principle that you can do with currently available technology, okay? So to finish here, so the future perspectives, I want to apply this in the study of condensed matter, atomic physics, and more. Maybe some spin models with many-body angular momentum couplings, okay? Obviously, the implementations in quantum computation and information, okay? And then in my poster, I will talk about the, if you are curious, I will, there's the other part of this work, is the implementation of these hypergraph states in D levels, okay? Measurements, I am constructing a scheme for handling measurements, okay? At least projective measurements, okay? So if you want to construct an entanglement witness or something like that, okay? Or measurement-based quantum computations. So I don't know if I have time for the questions, but we have the coffee break later. And okay. There's a last slide. I want to give my thanks to the organizer, participants, and UNB, this International Center of Physics, and the Institute of Physics for the hospitality when I was 3 months here as a visiting researcher, and for Finatech for the financial support, okay? And so thank you very much, and okay.
Thank you. We have time for questions. Okay.
Thank you, Frank, for this very interesting talk. Thank you for this very interesting talk. Better now? Okay. So I was wondering about the state of the art concerning the implementation of quantum computers. And I think they're mostly based on qubits. What's the state of the art now? And how to implement this qubits that you mentioned?
This D level, yeah. So that's my idea. At least I give this proof of concept. It's kind of a qubitization, we say, yeah. Like so, I'm using this qubit what is known in qubits to get this qubit stuff.
Well,
Okay, but the cost is like the number of modes exponentiate. Yeah, so I'm still there. Yeah, but there's another way that some other researchers also. When I was finishing this paper, the week before, some other people put a thing with angular momentum sum that I also thought. So you decompose like this. You can use this if someone made a qubit scheme. You can do encoding and get a qubit or qubits scheme.
Mathematically, it's
So
mathematically it's very simple and elegant, but in terms of implementation,
yeah,
I guess it's way more complicated.
Yeah, the difficulties are, I imagine they are immense, but I am theoretical, so, theoretician, so I don't care so much, but I care that in principle it's possible and there's a way, yeah, so at least, and this can motivate the experimentalist or because it's, for example, I say quadrupole here in a very loose sense. But this motivates the experimentalist. I want to do exactly this interaction. Okay, so I think it's worthwhile in some sense. Okay.
Okay, next question.
Hello, thank you for your talk, very nice. Could you tell me a little bit more about the cross-care gate?
Mm-hmm.
Okay, here.
Okay, yeah, this is Chomuda.
Yeah, this kind of decomposition, you did that, or is it quite common in literature?
Okay, I think it's not trivial, but it was early identified that not this kind of decomposition, but it's a little bit more complex. But the idea is the two-mode cross-care interaction is very powerful. Yeah. So and actually in Brazil we have people from UF, Federal Fluminense, Daniel Joss Brod, and there is collaboration with this Joshua Combs. They put down Shapiro, I don't know if you know, he said, no, you can't do this way, the control phase gate, which is the simpler, okay? I can go in Blackboard, it's very immediate that the control phase gates follow from this. But Shapiro was saying, no, it's not possible, but they show that there is a way, yeah, to do this with very high fidelity, yeah, this kind of gate. And if you have the control phase gate, some control gate, you can do some decomposition and obtain the others, yeah. So I don't know if I answered your...
No, okay, because I was wondering if you could, inspired by variational quantum algorithms, variational circuits in which you have parameters, in which you can control and choose these parameters accordingly in order to find your unitary cross-care. Okay, the idea of this kind of variational circuit is to shorten, diminish the length of the total circuit in order to do very few operations at the end.
Oh no, yeah. So my work, maybe I didn't say, but in the archive paper, I say this work is not. I'm not consider problems. It's an open problem how to optimize the constructions here, and how to consider noise or stuff like that, because it would be too much stuff for this paper, and I'm not so knowledgeable about this yet. I don't know if I will be, but I want to consider this later on.
Okay, yeah, that's
because
important.
It's very different the optimization, the circuit optimization, yeah. From the physical optimization, and there's questions, I think you have some work on this, yes? Like there's the time of the computation, there's the physical time, there's, you have to take all these into account to really seriously implement something, I guess. No?
Okay.
Even theoretically, I guess. Yeah.
Okay, thank you. So you can talk later.
Yeah.
Thanks.
Okay, so our time is out. Let's thank the speaker again.